Hello everyone. Today we will be doing part 2 of the emitter-follower transistor circuit tutorial. Last time, we provided an overview of the emitter-follower circuit, its uses, and overall properties. Then concluded with the biasing and small signal analysis, calculating the gain, input impedance, and output impedance of this circuit. Today we'll start with a step-by-step design of an emitter-follower circuit, which we will demonstrate in the lab. Then discuss an analysis technique called impedance reflection that can simplify the thought process of designing with certain transistor circuits. Here's the schematic of the emitter-follower circuit with the biasing network we discussed in part 1. We'll be using the 2N3904 transistor as I used in the common emitter demonstration. To start with, we need to come up with some requirements for our circuit. As this class of circuit is designed to produce an approximate gain of 1, with good buffering characteristics such as low output impedance and high input impedance, let's assume a few parameters for the system. There are many reasons to use a buffer, but one of the most important ones is when presenting a signal to an ADC. ADCs usually have some kind of sample and hold circuit on their inputs, which basically means there's a switch that connects the input voltage signal to a small capacitor internal to the ADC. The signal is periodically sampled by connecting the input signal to this small capacitor. Then the ADC disconnects the input signal from the capacitor in its hold configuration, where the capacitor stores the voltage that we saw on the input during the sample phase. Then the ADC converts the voltage on the capacitor over a period of time depending upon the ADC technology being used. What this does is causes short bursts of charge to be drawn from the signal source by the ADC, which will cause voltage drops due to the output impedance of the signal source. Most ADC chips don't have input buffers built in to separate the signal source from this sample and hold circuit. This is due to the fact that input buffers add noise, and in order to incorporate a low noise buffer on the input of an ADC, it requires additional power and cost. With greater power and cost, the lower in noise you want to go. So most ADCs leave it to the user to put their own buffering circuitry there, depending upon their needs. Users that require ultra-low noise inputs, and to which cost is no object, will put expensive, power-hungry buffers. Users that don't really care about the noise level will put a cheap, low-power buffer or use it without a buffer, accepting the resulting noise or errors. As a result, if you look at datasheets such as TI's 12-bit ADC 128S102, you'll see things like the ADC will deliver best performance when driven by a low impedance source. For the ADC 128S102, it says less than 100 ohms for the source. For Microchip's 24-bit MCP3564R, it recommends tens of ohms for the source. So we're trying to get some pretty low resistances on the output here. Let's assume a value of 50 ohms for our desired maximum output impedance. On the bright side, ADCs tend to have a rather high DC input impedance, so we will assume the load impedance is much higher than our 50 ohm target, so we can ignore it in the analysis. For the input impedance, let's assume the source has at most 1 kiloohm. You might consider this low impedance already, but there's only so much buffering that a single BJT can accomplish. A variant of this circuit using 2 transistors, in what is called a Darlington pair configuration, can help with this. We will explore the Darlington pair in later videos. So with the 1K resistance, we need the circuit to perform a factor of 20 reduction in impedance. According to the 2N3904 datasheet, the optimal collector current for maximum beta is 10 milliamps, resulting in a minimum beta of 100. However, 10 milliamps is a lot of current and we don't want to burn more power than we need for our buffer. And this will also result in a base current of 100 microamps, which will make our biasing resistors have to be smaller, which might reduce our gain too much. Let's instead go with 2 milliamp collector current, which has a minimum beta of 70, which should work better. To be fair, I did put a bit more thought into the 2 milliamp collector current decision, since we know the approximate minimum output impedance is constrained by the value alpha over GM, which is around 50 ohms at 500 microamps collector current. Knowing there will be parasitics and other things that drive that value up, having a collector current 4 times this minimum value to drop alpha over GM down by a factor of 4 made the most sense to me. We should still be able to meet our goals with 2 milliamps, However, we'll have to make sure that the swing in our output voltage doesn't drop the collector current below 2 milliamps, as changes in the emitter voltage will directly impact the collector current and thus the output impedance. To set our emitter resistor, we need a target output peak-to-peak voltage range. Going with our theme of driving ADCs, we'll set our requirement to match the voltage range for the ADC 128S102 with a 3.3 volt rail, which is a 3.3 volt peak-to-peak. Now we need a minimum gain. Let's assume we can accept a 10% error. There are many ways of mitigating gain errors, and let's say that our mitigation strategy allows for a 10% error, or a minimum gain of 0.9. So we should be able to satisfy these requirements with a single BJT emitter follower circuit. Let's start with setting VCC to 11.8 volts as we did in previous videos, as that's what my lab setup's positive voltage rail is. Now, in order to keep the collector current from getting too low, we'll want to push the zero input emitter voltage as high as we can so we can keep the emitter resistance high. The maximum emitter voltage we can use is actually essentially constrained by the base voltage. We know the peak-to-peak base voltage will be approximately the same as the peak-to-peak emitter voltage, as the gain is approximately 1. So we need the base voltage to be plus or minus 1.65 volts around some value. The maximum value of the base voltage needs to be less than VCC. More realistically, we'll want it to be less than about VCC minus 1 volt. Let's set that maximum value to 10.65 volts to simplify the math a bit. This makes the base voltage at zero input voltage equal to 9 volts. This in turn makes the emitter voltage at zero input about 8.3 volts, assuming an approximate 0.7 volt base emitter voltage. So now we need to think about the minimum output voltage to determine minimum collector current. Minimum output voltage is around 8.3 volts minus 1.65 volts, which is 6.65 volts. So we need to make 6.65 volts on the emitter produce our 2 milliamp minimum collector current. We're going to just assume beta is such that the collector and emitter currents are about the same. The emitter resistance required to produce 2 milliamps with 6.65 volts is about 3.325 kiloohms. The closest standard value I have is 3.3K, which will actually make the current slightly higher, which should account for the slight difference between emitter and collector current and generally make the circuit more reliably meet the requirements. So to accommodate our peak-to-peak output voltage, we should compute two collector currents and continue our design by being able to satisfy both collector currents. So minimum collector current is 2 milliamps. Maximum collector current occurs at the maximum emitter voltage, which is 3.3 volts higher than 6.65 volts, or about 9.95 volts. This results in a maximum collector current of about 3.02 milliamps. This is not that much higher than 2 milliamps, so this will hopefully mean the amplifier parameters won't change very much over our operating range, as the biasing point only changes by about a factor of 1.5 over our operating range. So now that we've gotten this sorted, we need to set our base voltage bias point, which we said was 9 volts. So first, to decide upon our biasing resistors, we need to think about our maximum base current. Using our minimum beta of 70, the maximum base current is our maximum collector current, 3.02 milliamps, divided by 70, which comes to about 43.14 microamps. As before with the common emitter, I'm going to use some fixed resistances as well as a potentiometer, which I will adjust while measuring the base voltage with a DMM so I can set it more precisely. But let's put a lower bound on the parallel combination of the biasing resistors for the purposes of our gain and impedance calculations. I'm going to assign it to be the somewhat arbitrary range between 20 kiloohms and 50 kiloohms. With 50K of biasing resistance, the total contribution to the base voltage due to the base current is equal to about 2.157 volts, which translates to a collector current deviation of roughly 654 microamps. Most of this deviation will be removed when I compensate for it with the initial setting of the base voltage, and the remaining deviation due to changes in input voltage will be significantly less than this, as beta will not vary all that much over the application output voltage span. So we should be fine. Now before we set the values for C-in and C-out, we need to calculate the small signal parameters for this circuit. So let's convert this to the small signal model. For the small signal analysis, we will assume Cin and Cout are sufficiently high to be treated as short circuits for all applicable AC frequencies. So here is our emitter-follower circuit, and we'll just quickly calculate the main small signal parameters. Transconductance is 76.92 millisiemens under minimum bias current, and 116.15 millisiemens under maximum bias current. For our design, it's best to get a conservatively low R-pi estimate, so we use the maximum transconductance. Similarly, the minimum RO is best. This way, under conditions with lower IC, these two parameters will actually be higher and thus less impactful on our circuit. Now we perform the appropriate calculations for the parallel values, and we see the following small signal circuit with real values plugged in. Note that I haven't used the minimum and maximum values, just the worst case ones for gain and input impedance. Technically, some of these values could be altered to make the output impedance worse, but under those conditions, the gain will be closer to 1, so for this analysis, we'll just use these values. Note that while I used the maximum collector current for R-pi and RO, I'm using the minimum collector current for the transconductance GM, as it will be used in other equations from now on. This should produce a mostly conservative worst-case estimate for both gain and output impedance, and will increase the probability that the design will succeed. So with these values, let's calculate the three central small signal parameters: gain, input resistance, and output resistance, using these equations we derived from the previous episode. For the gain, we calculate an approximate gain of 0.944, which is well within our requirement of 0.9. Our input resistance comes to approximately 18.29 kiloohms, which is pretty good, much higher than our source resistance. And finally, our output resistance is about 26 ohms, which is almost 50% lower than our requirement, which is great. Leaves some room for unexpected resistances within the transistor and in the wiring. So, some of you may have noticed that I haven't specified a required frequency range. We will specify one now. Let's set the requirement that the system needs to work from 1 kHz to 20 kHz. Let's move back to the overall circuit and decide upon values for our capacitors. So here we have the overall circuit. To determine the requirements on Cin, we need to take a look at how Cin affects the circuit. Cin effectively increases the source impedance by an additional 1 over Cins, and so to ensure that capacitance doesn't significantly affect our circuit, we must make it significantly less than Rs at 1 kHz. This is the conservative way to design Cin, but may not be practical for very low Rs. The more important factor is that Cin must be significantly less than Rin, as that's the impedance that it forms a divider with, causing a decrease in the gain. The capacitive reactance, which is just the impedance due to capacitance, for Cin is equal to 1 over Cin times 2 pi times the imaginary unit j times the frequency. The worst case frequency for this parameter is the minimum frequency. Rearranging this equation to solve for Cin, we get Cin equal to 1 over Zcin times 2 pi jf. We take significantly less than to commonly mean a factor of 10 lower, though of course you can calculate everything out by using the imaginary representation of Zc pi and adding that to Rs to create a new source impedance containing both, but it's usually good enough to assume a factor of 10 lower. So plugging in 100 ohms for our Zcin value and multiplying it by negative j to get it in appropriate units, the negative is due to the phase shift caused by the capacitance, we get a required capacitance of at least 1.6 microfarads. I'll put a 10 microfarad capacitor in for Cin to be conservative. For Cout, it's going to need to be a little higher. I'm going to do a slight reinterpretation of this target output resistance requirement and make it the magnitude of the output impedance instead. So we want the output impedance to remain less than 50 ohms even through this capacitor. In order for the output impedance to be less than 50 ohms, we need the capacitive reactance of the output capacitor, when combined with the output resistance, to be less than 50 ohms. But we also want it to be a bit lower to allow for some margin. So if we set that resistance to be 20 ohms of capacitive reactance at our lowest frequency of 1 kHz, we get a combined impedance magnitude of 32.8 ohms, using the Rout of 26 ohms we calculated previously, which leaves plenty of margin between 32.8 ohms and 50 ohms. So at 20 ohms, the required capacitance is 7.96 microfarads. I will put down 20 microfarads to make it conservative. So now that we have all the circuit elements defined, we need to place our test equipment on the circuit. So here I've placed a signal generator to serve as my input voltage, scope channel 1 measuring this input voltage before the 1K source resistance, scope channel 2 measuring the output voltage, and a DMM measuring voltage on the base to allow me to set the bias point with the potentiometer, which, as we recall, must be set to around 9 volts. Additionally, due to the input resistance of my oscilloscope being so high, I need to add a 100K resistor on the output so that the output can settle in a reasonable period of time. This will have a negligible effect on the circuit. So here's a picture of the circuit in the lab. Bringing up the scope, I've set my scope so that it's triggering on an external TTL pulse from my signal generator so that we can reliably trigger on low signal magnitudes. So first we enabled a function generator at 1 kHz with a low signal magnitude. The signals are very noisy due to the low signal magnitude. To mitigate this, we'll set the oscilloscope to average several sweeps, which will remove anything that isn't frequency locked to our trigger signal. And now we can see that the waveforms are much cleaner. Looking here, we see that the waveform in yellow is about 96.8 millivolts peak to peak, and the output waveform in blue is about 94.4 millivolts peak to peak. This results in a gain of about 0.975, which is well within our requirement of 0.9 to 1.1. Now let's check the gain at 10 kHz and 20 kHz as well. Increasing the frequency to 10 kHz, we see that the input waveform in yellow is about 96.4 millivolts peak to peak, and the output waveform in blue is about 93.6 millivolts peak to peak, resulting in a gain of 0.971, which is very close to what we had at 1 kHz. Finally, going up to 20 kHz, the input waveform in yellow is about 96.8 millivolts peak to peak, and the output waveform in blue is about 95.2 millivolts peak to peak, resulting in a gain of 0.983, which is again very close to what we had for the 1 kHz and 10 kHz. So this circuit appears to have a good gain across the bandwidth at small signal. Now let's take a closer look at how it handles a significant load in the form of a 100 ohm resistor on the output. Going back to 1 kHz, here we have the circuit with no load at an output voltage of about 94.4 millivolts. And now we add a 98.58 ohm resistor to the output and wait a few seconds for the averaging to stabilize. And we see that this load causes the output voltage to drop to 80.8 millivolts. We can use this resistance in a sort of crude way to determine the output impedance. With this additional resistance, we have effectively constructed this resistive divider comprised of the emitter follower's output resistance and this new load resistance, with the output voltage equal to the no-load peak-to-peak voltage, and the loaded voltage as the output voltage, which comes to this equation. Rearranging terms and simplifying, we get an output resistance of approximately 16.6 ohms, which is significantly lower than our calculated estimate. This does not surprise me, as our estimate assumed minimum beta, and with a much higher beta, the result is probably dominated by the alpha over GM term, which, at a 2 milliamp collector current, is approximately 13 ohms. Let's take a brief look at what happens at 20 kHz with this load to make sure it still works. So now I've removed the output load, and now I'm changing the input signal to 20 kHz. Which has a similar input and output voltage. And now I've put the resistor back in. It's right around 81.6 millivolts on the output. Still pretty similar, maybe a little higher, which makes some sense since the AC coupling capacitors will both have less impedance and thus produce a slightly lower output resistance. So we've looked at this circuit using a small signal, but we specified in our requirements that we want to provide a large signal. So let's see how that works out. So back at 1 kHz, I've gotten rid of the oscilloscope averaging because with the increased signal amplitude, I no longer need it to clean up my signal. I've set the peak-to-peak input voltage to be around 3.34 volts, so slightly more than our required 3.3 volt peak-to-peak signal, and we see about a 3.2 volt output. This results in a gain of about 0.958. Moving on to 10 kHz, we see the peak-to-peak input voltage is at around 3.32 volts, and the output is about 3.18 volts, only very slightly different. Moving on to 20 kHz, we see the peak-to-peak input voltage is at around 3.34 volts, and the output is at about 3.18 volts. So the gain is essentially the same. Basically, the gain differences are so small that they are in the noise, meaning that you can't tell the difference between actual gain due to changes in the circuit and the apparent gain differences due to electronic noise. So this works pretty well. The emitter resistance being relatively large mitigates most of the nonlinearity, and unlike with the common emitter, increases in the transconductance do not have a significant effect on the gain. They're more of a secondary effect, so this circuit is actually rather linear in the gain. Although I didn't specify that the circuit be required to drive low resistance loads, on the contrary, I sort of implied that an ADC interface doesn't need it, but let's see what happens when we put this 100 ohm load on the output in this large signal situation. So first, let's go back to 1 kHz and add that resistor back in. So here I've added the 100 ohm resistor, and it has completely messed up the output. So what's going on here? If you look at the output voltage, you can see that when the voltage flatlines, it's sitting at around negative 300 millivolts or so. The 100 ohm resistor is connected to ground, which means that when the output voltage is sitting at negative 300 millivolts, that current is flowing out of ground and into the emitter. This current is in the opposite direction of the BJT's collector current, and with this resistance, it's roughly 3 milliamps. This current exactly counteracts the BJT's collector current, resulting in the transistor effectively having a bias current of 0 and pushing the transistor into cutoff, where it can't really do much. The output capacitor is so large that it barely charges up before the input signal switches direction again and the cycle continues. Now let's verify that it does the same thing at 20 kHz. At 20 kHz, the output looks exactly the same, so it's not a frequency effect. Ideally, you would use more advanced methods of determining output impedance, like a sinusoidal current source where you measure the output voltage and current simultaneously using something more precise than this scope. But this test gives you a general idea of the properties of this circuit. Okay, now that we've done formal analysis on the circuit and seen it in action in the lab, let's talk about this concept of impedance reflection. Impedance reflection is an analysis method that allows a person to transfer resistance from the base to the emitter or from the emitter to the base in the calculations to simplify them or make them more understandable. What it really is recognizing that due to the mathematical relationship between base, collector, and emitter currents through beta, we can move resistance around in the system and get the exact same results. This method can make things appear more intuitive and make understanding the circuit easier for certain circuit configurations. Let's start by looking back at our hybrid pi small signal model. Here I have our small signal model with an emitter resistance, a base resistance, and an unknown connection to the collector. This is to show that this method works no matter what's connected to the collector. First thing we're going to do here is to use an alternate expression for IC. We know that IC equals GM VBE, but in this case it's more useful to use the equation IC equal to beta times IB, which we've done before. We can show these two equations are equivalent by noting that IB equals VBE over R pi equals beta over GM. Rearranging, we get GM equal to beta over R pi. Substituting that into the expression for IC, we see that we have VBE over R pi in there, which is equal to IB, and thus IC equals beta IB. Which expression is simpler to use in the moment is application specific, but they're both the same value. So we have beta IB equals IC, and since we know that IE prime equals IC plus IB, we get IE prime equals IB times beta plus 1. Again, I am calling this current IE prime, not IE, because the true IE incorporates RO. You might ask why I don't call the current through the current source IC prime instead of IC, to which I must admit that if I changed that now, it would make it too confusing, since that's not how I labeled it in earlier videos. So IC is the current through the dependent current source, IE prime is IB times beta plus 1, and IE without the prime is IE prime plus IRO. That's the nomenclature I'm going with. Now this is the important point. We have a fixed relationship between IB and IE prime. As a result, we can move our pi in the schematic so that it is in between RE and the current source so that IE is flowing through it. Note that the same voltage is dropped across this resistance as base is on the top of this resistance and emitter is on the bottom, just like with our pi. The only difference is that the current through this resistance is different, so we need to adjust the resistance to account for this. First, we note that our pi is defined as VBE over IB, then note that from the above equation that IB over IE prime is equal to 1 over beta plus 1. Now we note that this unknown resistance is equal to VBE over IE prime, which through some substitution and simplification we see is equal to R pi over beta plus 1. So here we see that a resistance in the base became a resistance in the emitter divided by beta plus 1. This is the power of impedance reflection. In many cases, it can significantly simplify the circuit. Note that the impedance is inserted in the emitter such that it's working within the loop formed by RO. Don't put it after the emitter where RE is. Of course, if you're working with a circuit where you're able to ignore RO, this simplifies things. With R pi, we can simplify the resistance even further by unpacking R pi and simplifying to get alpha over GM, which we define as the small signal resistance little re. This circuit is actually a different model from the hybrid pi model, called the T model, which is sometimes easier to use to analyze some circuits, but is mathematically equivalent to our hybrid pi model. As an example for how impedance reflection might be helpful to us, let's take a look at a circuit setup in emitter-follower configuration with a voltage source connected to the base through a source resistance, but is biased in such a way that any biasing resistors are large when compared with the source resistance or input resistance, which may occur for situations with high beta or with more exotic biasing circuitry. We also will connect the collector to a static voltage like we did earlier in this episode, and thus the collector is grounded in the AC model. First, we'll combine RO with RE in parallel to simplify the circuit. And now we'll reflect the R pi impedance into the emitter using our impedance reflection method, resulting in this circuit. However, we can go even further using impedance reflection to move that source resistance into the emitter using the same process as we did with R pi, resulting in this. With this setup, looking at just the gain, the calculation is trivial. We can ignore this current source since regardless of the current coming out of it, the output voltage is simply determined with the resistive divider equation, since Vin is on the top and ground is on the bottom, with Vout being tapped in the middle of the divider. This result doesn't look exactly like our previous result with the biasing resistors, but if we infinite value those biasing resistors, then simplify, then divide the top and bottom of the left portion of the equation by beta plus 1, and simplifying, we recognize that this is the same result as what the impedance reflection produced, with a circuit where the biasing resistors can be ignored. Output impedance determination with this circuit is even simpler. With the output impedance, we ground the input, which allows us to separate the current source and the resistances connected to the output node, allowing us to ignore the current source, as with the gain, and the solution is just this trivial resistor circuit, producing this output resistance. Looking back at the solution we derived previously that included the biasing resistors and infinite valuing those biasing resistors as we did with the gain, the classic solution simplifies to the result we just calculated when the biasing resistors are assumed to be large enough to ignore. In addition to moving resistances from the base to the emitter, we can also move resistances from the emitter to the base, which will help us with the input impedance calculation for this circuit. Moving briefly back to the circuit prior to any impedance reflections, we have Rs and R pi in the base, so to speak. All we need to do is transfer this Re parallel Ro resistance. So really all we have to do is the opposite of what we did with the moving of impedance into the emitter. So, recalling that IE prime is equal to beta plus 1 times IB, in order to reflect this resistance into the base, we need to find a resistance that produces the same voltage drop, but with only IB flowing through it rather than IE prime. This is, as you might guess, simply multiplying that resistance by beta plus 1. Resulting in this circuit. Once we're at this point, we can see that, similar to the output impedance measurement, we can separate the resistances on the input from the current source into these two circuits. Recall that input impedance is the impedance as seen after the source resistance, and so the input impedance is just this simple resistance combination we see here. Looking back at our previous solution, we see that it's a parallel combination of three elements, two of which are the biasing resistors that are not present in this example. So, infinite valuing those biasing resistors to get rid of them, we get the same result as we get in our impedance reflection. So we see that reflecting impedances from the base to the emitter and from the emitter to the base, depending upon the situation, can make solving an equation much easier. However, impedance reflection cannot be used effectively in all situations, mainly if RO is present and not connected to ground on one side, or if there's a parasitic impedance between the base and collector. For example, the mu capacitor that is present in the BJT high-frequency model. Those impedances can make impedance reflection not really simplify the circuit effectively. That concludes this video. In the next video, we'll look at the final fundamental single-transistor amplifier circuit, the common base configuration. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. If you have any comments or questions, leave a comment. See you next time.